Conference has every year, where we go. This year there were about 6,000 of us. We go, have 2 days of preparation, and then we go and speak with every single member of Congress. We spoke with all 4 representatives and our 2 senators this year. And we tell them about carbon fee and dividend, and we're starting to see a little movement in that direction. I'm going to let Gene introduce himself because he has he's a PhD from Cornell and such a background that I can't remember at all. And many of you know him better than you know me. So I'm going to let him talk. Thank you so much for coming.
Thank you, Shelley, very much. I'm glad to see some people here I've known for almost 60 years. Okay, is that appreciably better?
Yes.
Okay, and I'm glad, Janice just came in, and here's Mary, and Greta, and Wade, and Ron. And I think I probably left a couple out. I think John was going to come, people I've known 50, 60 years. For those of you who don't know me, this is the church I grew up in. I started in this church 10 years before it was here. When I started, it was the post office across from Collier's on Dixon Street. And it's really good to be back. I had a chance to visit my mother and father's grave, the other side of that wall, just a little while ago. I've been a PhD out of Cornell, which is where I met my wife, Jane. She was working on her PhD in environmental education. And mine is in resource economics, basically where electricity meets the environment. I've been studying global warming and climate change for 26 years. My epiphany moment came during my house husband year at a conference that Jane went to, and I got to hear Al Gore, Carl Sagan, and David Ryan. David Ryan changed my life. And I've been working to do whatever I can since then. I've probably bent your ear long enough. And I saw Mary raise your hand. Did you have a question?
No, I was just going to brag that there were just 50 year reunion people in here.
Oh, yeah.
Are you going to tell us who David Ryan is?
Yes, his boss was Jim Hansen. 1989. Already started playing. And I'll show you some of the slides that he showed me 26 years ago. So this is a bit of a summary slide. The important thing to know is climate change has been going on for millions of years. We've had this much CO2 in the air before, and what happened then is a clue to where we're headed now. That's something that very few people appreciate. Basically, Kansas was Las Vegas hot, Florida was mostly underwater. I think that's the best summary I can give. That doesn't play out instantly. Geology doesn't tell us how fast that happens, but it tells us it does happen. What we need to do is move beyond carbon neutral to carbon negative. Probably the best way to do that is to pay farmers and ranchers to take carbon out of the air and put it back in the soil. There are several other ways to do that as well. And we don't know for sure which are the most cost effective and which have the largest potential. But that's the name of the game. Getting our carbon emissions down to zero is easier. And we're making a lot of progress on that, actually. We need to make progress faster, though. So what I came to 3 or 4 years ago, before I ever heard of Citizen Climate Lobby, is a price on carbon, probably in this country, a carbon tax, which is probably a little simpler than cap and trade, which is the same thing. And the question is, how much money do you get back? 100% going back to the taxpayers is, I think, a really good solution. So some of the effects: rainfall, it's all about water and how water interacts with heat. There's a little bit more water in the atmosphere, a little bit more up the atmosphere, and wet places get wetter and dry places get drier. dry spells last longer, and the wet spells become more intense. So it's called drought and flood. A little review of the greenhouse effect. Your shortwave radiation comes in from the sun, visible light, long-wave infrared goes out from the earth. Some of it's intercepted on its way back down, and that's what heats up the earth more. This effect has been going on for billions of years, really. Solar changes are significant. The more significant one actually is the one that you don't think of usually, which is called the faint sun paradox. It used to be the sun was far fainter than it is now, and the sun gradually warms up. There are also sunspot cycles. They have some fairly minor influences. What we have here is, some of you have seen this maybe from, I don't know, Al Gore is, I think, one of the major people who use this, is over the last 4 ice ages, the relationship of temperature at the bottom, CO2 at the top, and CH4, or methane, in the middle. And you can see they're fairly closely related. The next slide, we'll go into that in a different set of axes. What this tells us in the past is there's a close correlation between temperature change and greenhouse gas changes. And you can also see that over millions of years, but it's more detailed here over just the last 400,000. So please bear with me. You have 5 slides in a row, which are really very intense graphs and data. So here's number 2. Now we're looking at the same data, but we're looking at it CO2 versus temperature instead of versus time. And what you see is there's a reasonably good relationship. R squared, for those of you who speak that language, is in the vicinity of 75 to 85%. 85% when you include methane. 75% if you look just at CO2.
You don't speak that language.
It's a strong correlation.
Yeah. And CO2 and methane are correlated with each other. Not perfectly correlated though. So trying to translate the temperatures that were measured at Vostok in the ice cores with the global average, I've chosen what we've observed over the last 130 years, which is North Polar region warms twice as fast as the Earth as a whole. And that's what this graph is based on. Down at the bottom, you see the CH4 data, not in italics from Vostok, and the extrapolation beyond Vostok, where we have more CO2, is in italics there. So I did a little multiple regression analysis with my Excel package, and that's the equation is green. It's probably the best of the 3. You get slightly higher R squared with a different formulation. That's the red line. Scientists generally prefer the logarithmic one. If you include just CO2, your R squared goes down substantially, and you're on a lower trajectory. What's really important is to see how this stacks up against earlier times when we had this much CO2 in the air, or 14 million years ago we actually had a little bit more, average about 450 parts per million. Today we're at 400, and 4 million years ago it averaged about 380 parts per million. The worrisome thing is that the CH4 methane levels have increased up until about 1950 far faster than CO2 levels had. Since then, they've increased actually a bit slower. We may be in for more trouble even than this graph would suggest because of the higher CH4 levels. And we're looking at, with today's amount of CO2 in the air, on the order of 4 degrees Celsius warming, maybe more. With the stuff we'll have 10 to 15 years from now, enough to make Kansas hotter than Las Vegas. But it plays out slowly, and there are chances that we can reduce those CO2 levels before it gets that hot. So that's really important. Okay, here's more of a text version of those same things. We have here the Keeling curve that probably many of you have seen, CO2 over time since the start of the Industrial Revolution. And it accelerated somewhat around 1950. About 1912, we passed the maximum between the last 6 or 7 ice ages. So what we're looking at now is really the highest level since 14, 15 million years ago. Deep ocean was 10 degrees Fahrenheit warmer, and seas were 80 to 130 feet higher, 25 to 40 meters for those of you who think that way. Almost as high, 4 to 4.2 million years ago. Seas were much warmer, not quite as hot, and sea level slightly lower than 14 million years ago, but not very different. So what that tells us is that most of Greenland's ice was gone, almost all of it, most from West Antarctica, and some from East Antarctica. You cannot get that much sea level rise unless that happens. And some people have seen that indeed there's sediments off the Antarctic coast that show that East Antarctica lost a lot of ice back in those days.
When it was 400.
400 plus, 450 especially.
Which is what it is now.
400 now, headed up. So there's a positive feedback mechanism. Ice melts, exposes something darker underneath, absorbs more heat, warms up more, melts more ice. The big thing is that very few people appreciate is their huge lag effects. What we've seen so far, which is about 1 degree Celsius warming, we're going to be seeing 4 times that much just from current CO2 levels. We don't know how fast those play in. 4 million years ago, they had a long time to play out. So far, we've watched a century, most of it in the last half century. Yeah.
Can we ask questions as go on, or is there going to be questions?
There'll be questions afterward. If you want me to hold it for 45, 50 minutes, it's probably best to hold the questions. What many people don't appreciate is global warming has accelerated in the last 15 years. It just went into the oceans. Instead of 85% of the heat going into the oceans, 94% has gone into the oceans. The ocean heat has penetrated down to at least 2,000 meters and probably farther. 2,000 meters is as far as we've been able to measure, though. The scope of it, 5, 10, 15, 20, what does that mean? Well, one of those little things is as much energy as the U.S. uses in 100 years. Here are some numbers about the acceleration over the last almost 50 years. And the acceleration of how much heat the ocean holds, which is basically how much heat the Earth holds courtesy of global warming, has really accelerated quite a lot, up 2.5 times in roughly 30 or 40 years. What that means is the oceans are gaining more heat every 2 years, every 1.5 years almost, than all the energy humans have used since 10,000 BC. That's a lot of energy. It's the momentum is far bigger than most people have any idea about. We're now going to take a look at the small subset that's the air at the surface, which is what most people think of as global warming. This is actually about 3 to 4% of the whole, but it's what people talk about when you talk about global warming hiatus from 1940 to 1970, or maybe 2005 to 2012. That's what people are paying attention to. And you notice there are ups and downs to it. A lot of those ups and downs, there are multiple factors, but probably the most important factor for the bouncing around is how much sulfate is in the air. And that's the emphasis of this slide. The data on sulfate in the air is not really good, but it's the best we have. It's easy to observe quite a few different volcanic eruptions, starting with Krakatoa. Here you have one in Guatemala and 3 in the Caribbean. Here you have one in Mexico and one in the land of 10,000 smokes in the Alaska Peninsula. And again, you can see sulfate cooling offsets greenhouse gas warming. Then you have a period without much sulfate cooling, especially in the Great Depression, and notice how the temperature jumps up. Then you switch to a lot of coal-fired power plants and the temperature levels off. You can see the eruption of Mount Agong in the Philippines in 1965 makes a big impression. And then the Clean Air Act, 1975, started to work its magic in the U.S. And you can see major rises in temperature. See a couple of volcanoes, including Pinatubo, not as strong as Krakatoa or even really Agong. What we're seeing is sulfates are still triple the levels at the start of the period. So there's a lot of hidden warming, even if CO2 levels stop. You get rid of the sulfur, which we'll need to do long before the end of this century, and you're going to see a fairly big bump up in temperatures as a result. So anyway, the basic message is, which I think most of you know, Earth is heating up. It's just 0.25%, but 0.25% is an awful lot. It's 50 times the global electric supply or 20 times human energy use. That's 0.25% of the general exchange of heat Earth with the rest of the solar system. It's been accelerating. Part of it, to regain equilibrium, it has to warm up another 0.6 degrees Celsius. That number is about 6 years old. I'm not sure. It might be a little more currently. Here at the land surface, 1.15, revised slightly down as a result of May data. 0.99 in the last 50. Here at the sea surface, basically 0.9, 0.68 in the last 50 years. I try to keep this updated when I can. But basically, the oceans have gained 10 times more heat in the last 40 years than all the energy humans have ever used. And that has been accelerating. So another different summary. Heating is differential. Land surface warms faster than the ocean surface. Warms more where it's coldest, winter, night, toward the poles. Warms faster in the United States and the world as a whole. And in the interior parts of the United States, far from water, it warms faster than by the coasts. So you've got enough CO2 now to make Kansas summers, Las Vegas hot, probably hotter. And the heat has been happening. 2 years ago, I spent about a year looking at temperatures for the U.S. and started out in 26 cities. Found this trend over that last 35 years. Looking at Salina, Kansas, in the heart of wheat country, near where my mother grew up. Lewis Fry, some of you probably remember. There was a cooling period, at least in the United States, and a warming period. Warming has been much faster since the eruption of Mount Pinatubo. If you focus just on the last 20 years, warming 12.5 degrees Fahrenheit per century, Las Vegas hot. Now we're going to look at Arkansas. Here's Fayetteville, that's the airport near Greenland. And what you're looking at is a lot of cooling. 3 degrees over 36 years, 13 degrees since 1993. Bentonville, that's the new airport, XNA, much shorter time series available. Very similar rate of warming in the last 20 years. Fort Smith, oh, it looks like Smith got cut off. Oh well, maybe it got cut off. Yep. Warming much faster. And it was especially hot in 2012, even much worse than Fayetteville. Harrison, a bit faster than Fayetteville. It's a little bit cooler to start out with. There's Little Rock. Little Rock is not warmed so fast. And the contrast between the 36-year record and the 20-year record is not as great. Russellville is also a new airport, fairly similar in record length to XNA, warming very fast, similar to Fort Smith. Average of 11 places in Arkansas. 4.1 degrees over 36 years, a little more than 11 degrees over the last 20. Tulsa is much like Fort Smith, except even warming even faster. It was at one point the third fastest of any place in the country that I looked at, and I've looked at 190 of them. So around Fayetteville, it's been warming very fast. That doesn't say how fast it's going to warm, but that says how fast it has warmed in the last 20 years. And it wouldn't surprise me if similar warming keeps up. There'll be a lot of variation from year to year, but the long trend is clear. Okay, this is, I later extended this from the original 26 cities to 128 cities, and added in 2013. My original analysis was before summer of 2013. The 2013 was not as hot as 2012, so the numbers came down. Warming is slower in the coastal areas, especially Pacific and Alaska. I was surprised about Alaska warming slower. But the Great Plains areas and Rocky Mountain areas have been warming very fast. And here's a little chart or table I prepared. Say how long till it becomes as hot as Las Vegas. I'm not sure I got Fayetteville on that table, but you see Fort Smith, 2054. Pine Bluff, on the other hand, 2111. Places in Texas get hot, Oklahoma. Salina, Kansas is hot as Las Vegas at this rate, 2073. Again, we don't know how fast it's going to warm in the future. We know there'll be a lot of variation from year to year, but this is sobering. Here's a report that came out a bunch of months ago called Heat in the Heartland, and it has some maps actually that are useful. On the left are average temperatures in the various states, and on the right are temperatures about 70, 80 years in the future for those same states. These are if current emission trends continue, although I would add that a lot of this heating is baked in even if we quit cold turkey. But if we don't quit cold turkey, it's worse. That much I can tell you. Okay, this is about temperatures and days over 95 degrees Fahrenheit. Maybe that's 35 Celsius, something like that. And how often they happen, and they happen a lot more often. You're approaching the levels from Las Vegas. And by the end of the century, according to somebody else's analysis, not mine, you get a fairly similar result that quite a few places may be just about as hot as Las Vegas, especially in the Ozark region, in Missouri, and a little bit of southern Illinois down by Carbondale. This is one of many takes of what might happen to the food supply, which I think is my biggest worry. And what you see in the rightmost pane toward the end of the century is 20, probably 30, 40, even 50 degree reductions in the major crops. Winter wheat actually does fairly well because it's not growing in the summer. But the crops that grow in the summer are hit very hard. It'd be, I think, much like what happened in 2012 when we lost a quarter of the corn crop and quite a lot of soybeans as well. So the best reservoirs we have, called reservoirs in the sky, they're glaciers. And they're dwindling. 30% of Himalayan glacial ice has vanished since 1980, which means rivers can vanish too. San Joaquin River already vanishes for a few months out of the year. I'll just say that. And the drought in Colorado River is now at 16 years. I haven't updated that here. The permafrost and to a lesser degree the methane hydrates on the seabed are the big time bomb. Permafrost, according to the only analysis I've seen of the future that's realistic, can add 100 parts per million of CO2 by the end of this century and 300 by 2300. probably will not add that much. That's in the business as usual case where we don't cut back our emissions. At all times, the permafrost emissions, at least in this analysis, are fewer than human emissions. And I think if we can get our own emissions under control, the permafrost is going to be a major problem instead of utterly huge problem.
What about the methane up there?
It's escaping 10 to 20% as fast as the carbon from the permafrost. The methane hydrates, you mean?
Yeah, especially those because they're pretty unstable, I think.
Well, you've got the seabed warming, but you also have the seas rising, putting more pressure. Those are offsetting influences, but on the whole, yeah, they will tend to come out of solution and rise. A lot of them dissolve in the water as you go up, but not all of them. And over time, a smaller fraction will. I spend a lot of time looking at ice on the Arctic Ocean. I update that every day. You don't see the daily updates here, but you should have some daily updates on your CV. This year was the earliest start of the melt season on record, and then it kind of petered out for quite a while, and then 2 weeks ago it started up in earnest, and probably about 2 days from now it'll be ahead of the record pace for the least amount of ice covering the Arctic Ocean since record keeping began. But it's not, the Arctic Ocean sea ice is really important because it changes how much of the sun's sunlight is reflected and therefore has a very fast feedback on temperatures. The other one is the ice on land in Greenland and Antarctica. That changes more slowly and you don't have as strong albedo effects. Between them, they cover about as much area as the Arctic Ocean. But what that does is it raises your sea levels. Right now, sea level rise is dominated by the thermal expansion of ocean water and by the mountain glaciers that are not Greenland and Antarctica. You're about getting to the point where Greenland and Antarctica are contributing about